Okay, here we go, chapter 21. This is nuclear chemistry. And I am Ms. Bedrosian, of course. So let's go over a few things about nuclear chemistry. A nuclide is a unique atom represented by, and it is A atomic mass, Z atomic number, and X is the symbol. And it's usually represented like that. You've seen that before. The term kinetic stability describes the probability that a nucleus will undergo radioactive decay. So whether or not it's stable or not. And there's some simple rules associated with that. Oh, that's kind of cool. Boom. That would be a quick radioactive decay. Now, if they are stable, they are said to be in a zone of stability. So how do you know if they're stable or not? Well, there's a couple of simple little rules associated with that. A, all nuclides with 84 or more protons are unstable. So that means the big fat nuclei, they're unstable. They're radioactive. Light nuclides are stable when Z equals A minus Z. Atomic number equals the mass minus the atomic number. And when the neutron to proton ratio is 1. Even numbers of protons and neutrons are more stable than those with odd numbers. I have no idea why. Actually, I might have an idea about that. Especially stable nuclides have magic numbers of 2, 8, 20, 28, 50, 82, and 126. Those are called the magic numbers. And here's a little cartoon. All right. So let's review the things that are involved with nuclear chemistry. An alpha particle is a fast-moving helium atom with an atomic mass of 4, 2 protons, 2 neutrons, no electrons. A beta particle is interesting because this is all coming from the nucleus. So this is what confuses a lot of people. This electron is from a neutron breaking apart. A neutron becomes a proton and an electron. The electron leaves the nucleus, and then the proton is there, and it changes the atomic number. A gamma particle has no mass, no charge. And here would be a gamma particle decay. It also gives off an alpha particle, and you could see that gamma looks like a Y, and it's 0, 0. No mass, no charge, no proton. A positron is kind of a strange thing. It is a positively charged electron, and that comes out of the nucleus as well. Please note that the atomic number changes when that leaves. An electron capture. This is when something gains an electron, but it's gaining it into the nucleus. So you shoot the electron into the nucleus. Please note it gives off a gamma particle and the atomic number changes. All right, let's do some half-life problems. Technetium 99 or technetium 99 is used to assess heart damage and decays by gamma emission. The rate constant is 1.16 times 10 to the negative 1 per hour. And you're going to have to find the half-life. Reminder, do you remember how to find the half-life? You should know this because we've done it in chem and you've done it in math. T half-life is 0.693 over K. And K in this, you can see with the rate constant right there. And so this came out to 5.98 hours. Not too difficult. Let's do another one. The half-life of MO99 is 67.0 hours. How much of a 1 milligram sample is left after 335 hours? You solve. Here comes the answer. I'm not doing it for you. The answer is 0.031 milligrams remains. And how did I do that? Well, I'll give you a hint. How many half-lives are in 335 hours? That's the hint. You figure it out. Now, the remnants of a fire from a cave showed a C14 decay rate of 3.1 counts per minute per gram of carbon. Fresh cut wood has a 13.6 count per minute per gram carbon. You're going to have to calculate the age of the remnants. You probably need to know the half-life. Half-life of carbon-14 is 5,730 years. Now we're going to go back to things we've already learned before. Decay rates are directly proportional to the number of carbon-14 nuclides. So, what kind of kinetics is it? It is first-order kinetics. So rate equals Kn, and n is the number of nuclides. So let's take a look at the rate. .1 counts per minute gram equals the rate at time t. That would be Kn. And the 13.6 counts per minute per gram is the rate at time 0. So Kn 0. If you can, divide those so we can get a number, n over n0. That equals to 0.23. Now let's go to that integrated rate law. Well, the first order rate law. And that is, do you remember? The natural log of n over no equals negative kt. If you pause and solve now, go for it. Here's the hint. Solve for k first. Try pausing again if you're stuck. Do it again. All right, here comes k. I'm not even going to show you k. The final answer is 12,000 years. You need to solve for k first, and then plug it all back in. You'll get 12,000 years. And here's a joke on carbon dating. Now guess what? It's the end of it all. This is it. Last lecture. I'm not going over anything else. Hallelujah. The rest will be lectures in class. Okay, here we go.